In this video, we're going to look at how to represent voltaic cells. And this is just a continuation of 20.3, but all of the lists that we look at and examples that we look at aren't in your book, so this is going to kind of be its own separate video. And when we represent voltaic cells, we're going to look at both the shorthand notation on how to represent a voltaic cell and also how to draw the voltaic cell. What we're going to look at first is the shorthand notation for representing a voltaic or galvanic cell. Remember, those two terms are the same. We can actually describe a voltaic cell using a line notation that's based on these three conditions. So a single vertical line indicates when you have a change in state. Typically that is reactants and products. So you use a single vertical line to separate your reactants first, then the single line, and then the products. If you have an aqueous solution, you need to represent the concentration in parentheses after the symbol for the ion or the molecule. And we're going to look at an example of that. If you're not given the concentration, assume it's 1 molar, because 1 molar is your standard concentration. If you have a double vertical line, that's used to indicate the salt bridge. So it's basically separating one half cell from the other. So the double line represents the salt bridge or the porous disk or the porous membrane. And then the line notation for the anode is always written before the cathode. So essentially what you're doing is you're representing the electron flow, because remember, electrons flow from the anode to the cathode, so from oxidation to reduction. So this is what your shorthand notation would look like. M just means metal, so you'd have your metal 1, a single line, and then your ion, because remember, this is the anode first. So you represent the anode first, so this would be reactant and product. Then you do the double line to represent the salt bridge, and then you do the reactant of the reduction. So it's going to be the ion, and then usually it's the metal. Again, this is the electron flow. So you have reactant, product of the oxidation reaction, reactant, product of the reduction reaction. So we're going to just look at an example together. So it says write the line notation for the following. So we are given a complete voltaic or galvanic cell right here. Notice you have the light bulb, it's lit up because this is a spontaneous reaction. So there are some steps that we have to do as we want to write the line notation. First thing you want to do is figure out what is the anode and what is the cathode. And there's one of two ways you can do that. You can look at the electron flow, because remember, electrons always flow from anode to cathode. Or you can look at the half reactions, because you're given the half reactions here. So we have electrons flowing from the right to the left. So that means that the zinc is actually our anode, the copper is our cathode. So we've determined the anode and the cathode, then determine the reactants and the products for each. Notice you're given the half reaction, so you're actually already given the reactants and the products. An extra step is already done for you. So here's a reactant and a product of the anode, reactant and product of the cathode. We ignore the electrons right now. And then what we want to do is we want to write the anode, then we want to write the cathode, and we want to include concentrations when needed. So when you have an aqueous solution, when you have an ion, you want to include your concentration. Now notice that we're not actually given the concentration here, so we're going to assume that it's standard and that it's 1 molar. So here we have zinc as a reactant, zinc solid. The zinc ion is the product. This vertical line represents a phase change. Right, so it represents the phase change between the solid zinc and the solution. This is the anode. The electrons flow from the anode to the cathode, but the double line in between represents the salt bridge. Then we have the cathode reactant, which is Cu2+. It's 1 molar. Then we have the vertical line. The single line represents us going from aqueous to solid, and the Cu solid is the product. So this is how we would represent this voltaic cell using line notation. I want you to now try to write the line notation for this voltaic cell. Again, go through the steps. Start by determining the anode and the cathode. So look at either the electron flow or the half reactions. Then determine the reactants and products for each, which you're actually already given via half reaction. Then write the anode, then cathode, and include your concentrations when needed. Now, this is going to be a little bit different because you actually have a gas here. So I want to just talk about what this means. This is an electrode. This is more than likely a platinum, a PT electrode. You need a platinum electrode when you have gas involved. So this platinum electrode actually allows for the reduction of the H plus to become H2. This is called a standard hydrogen electrode. And again, this is more than likely platinum. So pause the video, try this on your own. So here's what we get for the line notation. We have zinc and zinc 2 plus. Okay, this is the anode. Then we have the double line representing the salt bridge, represents the junction between the two beakers. Then we have H plus, that's 1 molar, going to H2, which is 1 atm. You also need to include pressures if you have gases. So you need concentrations if you have aqueous solutions, you need pressures if you have gases. If you have questions on this, write your questions down on the side, and then we'll go through your questions in class. So then we're going to look at how to actually draw a voltaic cell. So we looked at representing the voltaic cell using shorthand notation, but now we're going to look at how to actually draw them, because I'm going to ask you to draw a voltaic cell based on given information. So when you're drawing a voltaic cell, you need to include a beaker for each half reaction. So you need the anode beaker and the cathode beaker. You need an electrode for each half reaction. So whether that means you have a strip of metal or a platinum cathode for hydrogen. Then you also need to include the substances involved. So make sure you label the strip of metal, make sure you label what's in solution. You also need a wire connecting the two. And typically with the wire you also have a voltmeter or a bulb. And then you need to show the direction of electron flow in that wire, because remember, the flow of electrons is what gives us electric current. And then you also need a salt bridge, typically with Na plus and NO3 minus ions or other spectators. So maybe you want to include potassium and nitrate. But typically it's always nitrate because you always need something to be soluble. So now with this example, we're going to do this one together. This is draw a voltaic cell given the line equation. Assume standard state, which means 1 molar. So here you're given the shorthand notation. So you now need to be able to go backwards from the shorthand notation. So first what I would do is label everything that you know here. So what I mean by label what you know is what always comes first in the shorthand notation. Well, the anode always comes first. So this is the anode, and then the right side, this is the cathode. So that means that we have lead and we have silver at our anode and our cathode. So as you go through, we're going to go through the checklist. So first thing you need to do is draw a beaker for each reaction. So we can draw a beaker for the anode, we can draw a beaker for the cathode. Then we want to draw an electrode for each. So what that means is we're going to draw a piece of lead in the anode beaker. We're going to draw a piece of silver in the cathode beaker. Then we need to connect those electrodes with a wire, and we need to show the electron flow. And then we want to make sure that we show the salt bridge. So this is what we have. We have 2 beakers, we have silver, we have lead. Make sure you just label them. If you put lead on the left, that's fine, as long as you label. But I'm showing the electrons flowing from the anode to the cathode. Notice I labeled both electrodes. And then you also want to label what's in solution. Now, this is NO3 minus. You don't need to show the nitrates in the beaker. You do need to show the nitrates in the salt bridge, though. So really in the solution, what I'm focused on is PB as the anode, and Pb2 plus in solution. Then I want Ag as the cathode and Ag plus in solution. And then in the salt bridge we have Na plus and we have NO3 minus. What I want you to remember is that the Na is going to go toward the cathode, the NO3 minus is going to go toward the anode. And then also think about what happens in oxidation. So remember, this is the anode, so this is the oxidation. In oxidation we go from Pb to Pb2 plus. So the lead is actually going to come off in solution as Pb2 plus. And then for the reduction on the cathode, okay, make sure you're labeling everything. This is actually going to go from Ag plus to Ag solid. So this cathode is actually going to increase in mass. We're going to get more silver plated onto here. And the lead, we're going to actually lose some of this because it's going to come off. So this is actually how we go through and how we draw our voltaic cell. So here's another example. Given the following, what is missing? So I want you to take a look at this picture. What is missing from this picture to make this cell work properly? Well, it's the salt bridge. We're missing the salt bridge that belongs in between the 2 beakers, because remember, the whole point of the salt bridge is to maintain electrical neutrality. If this salt bridge isn't here, then cations and anions can't flow, which means your electrons aren't going to flow. So then B says list the anode and the cathode and indicate how the ions in solution move. So what can we look at to figure out what the anode and what the cathode is? Let's look at the electron flow. It flows from the anode to the cathode. So aluminum is the anode, cobalt is the cathode, and then remember that your cations move toward the cathode, your anions move toward the anode. C says write the overall chemical reaction occurring. So before we need to write the overall, we need to be able to write the half reactions. So we need to make sure that we know what's happening at the anode, so it's oxidation. So we have Al going to Al3+, and then at the cathode we have CO2+ going to CO. Now what you need to do before you can write this overall reaction is write each of the half reactions, figure out how many electrons you have, make the electrons equal, and cancel them out, just like we did with balancing redox reactions, because that's all this is. All this is redox. And then D says write the line notation for this cell. So remember what always goes first? The anode goes first, you need a double line to represent the salt bridge, and then you write the cathode. So this is actually what we get. Remember, anything that's aqueous needs concentration. If you're not given the concentration, assume that it is standard, which is 1 molar. And then given the following, A says list the anode and cathode, indicate the direction of electron flow, write the anode reaction, cathode, and overall, and write the line notation. So I want you to actually try this on your own. I want you to represent everything, work through this problem, and then we're going to go through this in class. I want you to really focus on what is happening at the anode, what is happening at the cathode, and I will give you a hint on this one, is the K+ is going to go toward the left, the SO42- is going to go toward the right. So that's going to give you your hint as to tell what is the anode and what is the cathode. So try this, and then we'll go through this together tomorrow.